do this with my Surface that I have for teaching, and unfortunately Zoom doesn't like that because it doesn't think of it as a tablet. It thinks of it as a computer, and you can't have two computers logged into Zoom at the same time. So I'm working on this. The college has some writing tablets available, and I've been trying to get a hold of one, which is surprisingly difficult because the people in the dean's office don't seem to know what they're supposed to be giving out. The IT people aren't in there that are giving it out. So anyway, I'm working on that. So in the future, hopefully this won't all be PowerPoint, but for now, I've tried to set it up where we just step through PowerPoints with a bunch of steps, and we'll talk it through as we go. All right, let's go ahead and get going then. Okay, so here's our first problem on dimensions, right? So you guys had a problem last week on the homework. We will see this again just moving forward in general. So I just wanted to go over some of the basics here. So the question here, the problem that we have in front of us is determine the dimensions in both FLT, so force length time system, and MLT, mass length time system, for A, the product of force times volume, B, the product of pressure times mass divided by area, and then C, the moment of force divided by velocity, okay? The first thing that I wanted to tell you was that in your online book, you're gonna wanna go to table 1.1. So I apologize, this is a little bit small, but what I did is I just went and grabbed screenshots of what basically is sort of a long table. And so I cut it into two pieces. And so this is, the bottom's on the right, the top is on the left. But essentially, this is the place where you're gonna find these FLT representations of dimensions for each one of these things, and then also the MLT representations, all right? And in particular, for part A, we're going to use, force times volume, all right? In part B, we're gonna end up using area, mass, and pressure. And in part C, we're going to use velocity and moment of a force, and then we'll also have, just those two. One thing that I wanted to point out, though, is that force here, you can see the FLT obviously is just F, and then in the MLT system, that's mass length per time squared, right? And so one way that you can always remember that is if you just remember that force is equal to mass times acceleration. Acceleration is always length per time squared, and then the mass, of course, is in mass units. So when you put those dimensions together, it should always be mass length per time squared, right? So that should work out.
Professor, I had a question.
Yep.
So when should we use FLT?
So in this case, hey, all right, I'm just going to go ahead and mute people if we're getting extra noise. So Mohammed, essentially, if you're just looking, in a way, it doesn't matter. You just can't mix them, right? You just need to be careful about not mixing them. And so if you are up against a problem and you aren't quite sure how to move forward with it or whether it's going to work out, then working either in force or in mass should work out or should be fine. What you'll see when we work through these three examples is that sometimes one can be a little more simple than the other, but it will sort of depend on which factors you have involved. So let me go through a couple of examples here, and let's just see.
But like as an end result, they will all have the same.
Well, they should all work out, but one would have units of mass, dimensions of mass, and one will have dimensions of force. You'll just see that some are simpler because remember, force can be represented as mass as well, but also it includes length and time. And so might just be a little bit more complicated is all. So that's all. So let me show you as we go through these. Let's see what happens. Okay, so let's just take part A and we'll work through this. So we said the product of force times volume, so force is represented by F. Volume in the FLT system is just length cubed, of course. That'll be the same in the MLT system. But essentially, if we're just going to take the product of these two, then we just end up with force times length cubed or force times volume, force times length cubed, and that's our solution, right? So that's fairly simple, Mohammed, for example. And we'll compare that in a moment to what happens on the right-hand side. Excuse me, on the right-hand side, force now is represented in the MLT system as mass times length divided by time squared or times time to the -2. And then volume, of course, remains length cubed, right? And so when we multiply these together, we're now looking at our solution being something a little bit different. Now, all I've done is put these together. We can obviously simplify that, right? I probably should have put parentheses around the MLT to the -2 and then another grouping of parentheses around the L cubed to just note that this was the force times the volume. But if we boil these down together, we simplify to basically what looks like this. The L here groups with these other three L's to give us mt to the -2, L to the 4. Now, it does not matter if I put the L before this. It could be ml to the 4, t to the -2. That's okay. We're not trying to apply any of, if we have superscripts here, these powers, we're going to need parentheses if we are going to apply it to anything more than what is immediately indicating, right? So we're not applying the -2, for example, to the m, only to the t. All right, so there's our solution there. And so, Mohammed, just in your response to your question, you can see that these two are different in their complexity, but it might also depend on whether you are given, the force in which something is happening or just the mass, right? If you don't have the acceleration, or if you're working with gravity, then you know the acceleration. But if you just need to work with the mass, you can just do that. All right. Either way, it should be fine. And so these two are equivalent, essentially. That's the other thing that you should note. They're not necessarily going to come up with the same number because force is represented slightly differently here. I guess I shouldn't say that. They would come up with the same number as long as your acceleration over on this right-hand side is gravity, right? Because that's what this force, I'm sorry, I am speaking a little out of turn. I keep thinking about our simple systems of statics. These should come up, if you are given the right information, these should come up with the same numbers. It just depends on how you've populated them and what you're given to get there. Sorry for the confusion. That was a very simple question, Mom. It got me thinking about that. So. All right, part B, the product of pressure times mass divided by area. In the FLT system, the force length time, pressure is in force per length squared. Mass is in force per length times squared. Yep, that's right. And area is in length squared. Okay? So when we put pressure times mass divided by area, then essentially we're just going to combine these as here's our pressure component, right? Here is the mass component, and here is the area. So now we have to do some combining and simplifying. So the two forces are going to come together to give us a squared. Length -2 and length -1 will combine. They will have to interact with this length squared in the denominator as well. And then time won't change, right? There's no other times in here to simplify with. So we put all this together and we simplify by one step. We're going to simplify further. But here's 4 squared, length to the -3. So I've just combined these. Length, time squared divided by length squared. And then we basically end up with the most simplified version of this is 4 squared, length to the -5, t squared. Okay, time squared. And then similarly, now this gets easier over on the mass side, only because when we look at the MLT system, only because now we remember we don't have a pressure involved, a force involved in this, but pressure now is still force per length squared. So pressure in the MLT is m L to the -1, t to the -2. Mass is just m, and then area is L squared. So, it just kind of depends here whether you want to work with this in terms of mass and this a little bit messier, or this very simple and this a little bit messier. But either way, they should all work out just as a little bit tedious, perhaps. I shifted this down a little bit just because of all the room this took up, but still pressure times mass divided by area. When we plug all of these in, we see our grouping. So here's pressure, here's our mass, we divide by area, and we basically simplify here in the numerator. And then when we combine with the denominator, we simplify to that value there. So m squared, L to the -3, t to the -2. Okay? Any questions on these? Maybe I'll go through the last one here and then pause for questions on the dimensions. Now the moment of force divided by velocity. All right, who remembers from statics or dynamics, if you're taking that now, what a moment is? Do you recall what the moment of force is?
It's like torque.
Sorry?
The torque.
Yeah, like a torque. Okay, but what would that be in like dimensions? Like what are we multiplying?
The perpendicular distance from the force, right?
Yep, times what?
Distance.
The distance
Times
times the actual force. Yeah, exactly. So it's the length times a force, essentially. And so the moment of force then has dimensions of force times length in the FLT system. The velocity, of course, is length per time, right? Meters per second, miles per hour, whatever. So moment of force then divided by velocity would look like this: FL divided by LT to the minus 1. And so we're going to simplify here. Mostly the L's are going to cancel, and the F and T are basically going to come together to give us F times T, right? T to the minus 1 in the the denominator puts it in the numerator without any, just to the 1 power, right? So, so there's our solution for the left-hand side. And on the right-hand side for the MLT system, we now take our moment force. Now this is a little bit different, so it's a little more complicated. We've got mass length time to the minus 2, and then that length. So the first grouping is force, the second grouping is the length for that moment of force. And then our velocity remains LT to the minus 1. So now when we group these or work through this, this quotient here, so now we've got MLT to the minus 2 times length in the numerator, and then in the denominator, we just have our length over time, or LT to the minus 1, which is velocity, recall right here. And we can now simplify, so we're going to multiply this guy in. So we get mass length squared T to the minus 2 divided by the length T to the minus 1. And then we take it a step further, and we can simplify all of this down to M. This L squared gets knocked down to L to the 1 because of the L in the denominator. And then T to the minus 2 here gets modified to become T to the minus 1 because this minus 1 is in the denominator and helps out that in the numerator. Okay, so those are our two solutions for part C. All right, any questions on this problem?
I mean, I just have a question with notation. Like, do you mind if we just put ML over T instead of writing MLT to the negative 1?
No, that's fine. Yeah, you can do fractions if you want. I was trying to keep it kind of concise on these slides. That's okay. Okay, let's move on to unit conversions. And in particular, I chose this one because it's one that you're likely to come up against often. Water flows from a large drainage pipe at a rate of 1,200 gallons per minute. And sometimes, by the way, that's represented GPM. You'll see GPM sometimes instead of gal divided by /min. So GPM, 1,200 gallons per minute. What is the volumetric flow rate or volume rate of flow in A, cubic meters per second, B, liters per minute, and C, cubic feet per second? Just another note, the cubic meters per second is sometimes called a cubic. I'll try not to use that shorthand notation unless we are, already familiar with it. I'm introducing it like the way I am today. And then cubic feet per second is often referred to as CFS. And the reason for that is simply that this is actually a very common unit used by the U.S. Geological Survey, for example, at their stream gauging stations around the country. So there's one on Boulder Creek, for example, at right above 75th Street Bridge that, you could go online and look at what the discharge is right now. How much flow is going by in the river is reported in cubic feet per second. It's just kind of their unit of standard. All right, so let me just introduce two things to you from the book. The first one is there's this nice figure 2 that kind of gives you some for what on the length. We have length on the left, mass in the middle, and force on the right. And just looking at these different, what is equivalent with respect to the different unit formats. And then what's more important for these is going back to the appendix. So this is a table E.2. So table E in your book is actually a bunch of subtables. So table E1 is over here, and it's time conversion factors. Table E2 is length conversion factors, and so forth. And here's a little key on how to use these triangular tables. Essentially, you're going to go look for something on this side and then work across and try to match it up with something from this side. But you can see, for example, sorry, I have to zoom in on this. For example, a foot, there are 304.8 millimeters per foot. So one of the nice things about these is that they do, sometimes you're just left with like a number of 304.8 and you're like, well, does that mean the millimeters go over the feet or the feet go over the millimeters? I mean, obviously in this case, we know what that is, but with units that you may not be familiar with, that might be a little bit tricky. So these units that they've put in are actually quite helpful to us.
I have a question.
Yeah.
Should we get used to using like tables like this to find our like conversions, or is it okay to just use Google?
Yeah, you can use Google if you want, and in particular for something like, you want the conversion from liters to cubic feet. That's fine. But I'm going to show you a shortcut in a moment where using these tables will be easier. So just hang on for that. The only other thing I would say is that all of these are probably going to be for like standard, like when it comes to volumes of water, for example, those are going to be at some standard temperature. If you need to start looking at something that's occurring at like 100 degrees Fahrenheit or 150 degrees Fahrenheit, something like that, there are some other plots in your book, in the ebook and I didn't give you an example of one, but they'll basically show curves with temperature on the x-axis that you would look at, say, I don't know, whether it's density like we've looked at before or viscosity or something like that. So just as a heads up there. Okay, so water flows. So let's just take part A. We need to convert 1,200 gallons per minute to some number of cubic meters per second. So in your mind, you're probably already thinking, all right, I need to convert gallons to cubic meters and also convert minutes to seconds. The latter of those two is pretty easy. Most of us should probably know by now. There are 60 seconds in a minute. But what do we do about those gallons? So you could go to those tables or Google and just look up how many gallons are in a cubic meter. If you inspected those tables a little bit, you would actually find that there is a direct flow rate conversion. So one of those subtables in table E looks like this, and these are volume flow rate conversion factors. So what you can find then, I should have animated this, I suppose. We had gallons per minute. So here's gallons per minute in the top, and here's cubic meters per second. And they tell you that there's 15,850 gallons per minute in 1 cubic meter per second. All right. So now what we could do, instead of making 2 conversions, we could just make 1, and we could set this up to say 1,200 gallons per minute times. And now note that what I've done is put gallons obviously to be in the denominator so that it cancels correctly with this. And if I had worked this out, I didn't take it further, but the minutes obviously would go in the numerator and they would cancel with that and we would end up with meters cubed per second. But you basically take 1,200, divide it by 15,850, and you end up with 0.0757 cubic meters per second. I'm just going to take that one step further and turn it into a scientific notation here. So you could show this in either way. And the one thing that I haven't emphasized yet that I do want to I want to get across, by the time we get to week 3, so not this current homework, but the next one, you will need to look out for your significant figures. Okay. One point that I want to make though is that there is a really nice primer on significant figures in your book. So take a look through that, work your way through it, and just make sure that you're comfortable with what happens after you take 2 numbers with different significant figures and you multiply them, you add, you subtract, you divide, whatever you do, what does that mean for your resulting number, okay? When we get to scientific notation, it's kind of easy to work with 3, but even that may be too many depending on the numbers that you put into your calculation. All right, so there's our final answer for this. We can also consider this from the, I don't know why that came in. Sorry about that, little errant there. We can also look at this then for part B, we were asked for liters per minute. Okay, so the first thing, we need to convert gallons to liters, but the conversion of minutes to minutes obviously doesn't have to happen, right? We already have minutes, so we really only need to convert one of these units. And in this case, it's the volumetric unit of converting from gallons to liters. Now, in this case, I can't remember if I used your table. I think I did use the table, actually, to find this. So table E, I think, .2 was this one, where I got 3.7854 liters is in 1 gallon. And so, and again, I've set this up so that the gallons will cancel, and we'll end up with liters per minute. Okay, so liters in the numerator, minutes in the denominator. When we do this math, we end up with 4,542.48 liters per minute. So that's fairly precise. However, we don't, if I wanted to round this a little bit just to be a little more general, I might just go to the tens place and say that I have 4,540 liters per minute. From a perspective of using our significant figures, this would obviously be 3 significant figures in this case, indicating that we were, compared to trying to advocate for 6 over here on the left-hand side. But I have used 1, 2, 3, 4, 5 in this. So think about what happens when you have 2 over here and 5 over here, and what result that gives you. So I just offer that as you think a little bit about going through that summary of our significant figures approaches, if you're unfamiliar with that or uncomfortable with it or need a little bit of a refresher. So that's available to you in the ebook. All right, the part C of this, recall there was one more conversion we wanted to make, and that was to cubic feet per second. So now we've got our flow rate of 1,200 gallons per minute. How do we convert to cubic feet per second? Well, we can convert the gallons to cubic feet and the minutes to seconds. We could also just go back to the that flow rate chart and probably find the one we need. I did this the hard way. So here I've identified that there are 7.48 gallons in a cubic foot, and there are 60 seconds in 1 minute. So the minutes are going to cancel here, the gallon units are going to cancel, and if I work through this math, I end up with a value of 2.67 cubic feet per second. Okay, so when you take 1,200 and divide it by 60, and then also divide it by 7.48, you should end up with 2.67. And that's our final answer on that. All right, any questions on how to work with those? Something you guys have had a lot of practice with already in your careers.
For like showing our work and stuff, what I'm getting from this is like, if we can like find something like where it converts gallons per minute to cubic meters per second, it seems like there's not a lot of work to be shown there.
Right. So part of the key there is if you were going to do like the way we did it in part A, that's fine, but just still show us your work, right? I mean, what we want to know, so if you mistyped something in your calculator or however you do your calculation and you have the wrong answer there, but you have the correct setup in the previous step with the right conversions, even if it's the flow rate rather than doing it, the time and then the volume separately, you'll still get credit. But you won't get credit if you don't show us how you got there. Does that make sense?
Yeah, that makes sense.
Okay, perfect. Okay, now something you guys maybe haven't dealt with quite as much, something a little more specific to fluid mechanics, thinking about the specific weight, density, and specific gravity. So this is fairly straightforward in the sense that if we have 1 cup of cream having a density of 1,005 kilograms per cubic meter. Remember, water is 1,000 kilograms per cubic meter at 4 degrees centigrade. Then this is going to be pretty close to that, right? We have 5 kilograms more, so it's pretty close. So if it's turned into 3 cups of whipped cream, right? So we go from the liquid cream to the whipped cream. Determine the specific gravity and the specific weight of the whipped cream. Super simple, right? It sounds very simple. All right, so we've taken 1 cup of liquid, we've introduced a bunch of air, meaning we've whipped it, right? And we've changed its context a bit, right? Now it's kind of this semi-solid thing, and it probably doesn't flow as easily and so forth. So now it's got a new volume, which is 3 times larger. What is the specific gravity and the specific weight of this whipped cream? So we have equations, as you may recall from last week and the week before. We talked about specific gravity, we talked about specific weight, but we did both of those in terms of density. So one of the things that we could do is simply figure out that we're given the density of the fluid here, right? That it's 1,000 kilograms per cubic meter, but we're not given the density of the whipped cream. So one thing we could do is try to figure out that whipped cream density. So we could calculate the density of the whipped cream. And one question we should ask is, do we have enough information for that? All right. Prior to it becoming whipped, we have both the density and the volume. The volume is 1 cup, right? And so one of the things that we could do is figure out the mass of the cream. Because after we've whipped it, the mass should stay the same. That is, the air we don't expect that we've whipped into the cream is really that heavy, right? Okay, so let's go ahead and do that. We know the volume of the final whipped cream, 3 cups, and we know that we started from 1 cup of cream, so the volume, and its density at that time was 1,000 kilograms per cubic meter. So first we could calculate the mass of the whipped cream. And by the way, I should note here, because this might be an obvious one to some of you, there are going to be multiple ways to solve these problems. The way I'm showing you is not the only correct way, but I am just trying to go through kind of a straightforward thought process. You might be able to find ways to make this more efficient, and that's totally fine. As long as you justify your work, it doesn't matter that much. But you do need to justify every step and not skip too many to try to get from one to another to demonstrate how you've gotten from one step to another. All right. So in this case, we're going to do this the long way, but we know that the mass of the whipped cream should be equal to the mass of the cream before we whipped it when it was still liquid. All right, so to calculate the density of the whipped cream, let's start with the mass of the whipped cream and then divide by the whipped cream volume, which was 3 cups. And so we're going to take the mass of the whipped cream is equal to the mass of the cream is equal to the density of the cream that we started with as a liquid times the volume of that. And by the way, one of the things that I'm trying to do here is show a capital V with a line through it. That's commonly used as a symbol for volume. And in fluid mechanics, this will become a little more of an issue in hydraulics, but we may be dealing with velocity. And so rather than confuse you between volume and velocity, where we might use capital V's for both, we try to put this line through the V that represents volume. I'm not sure why. It was the way I was taught. It's customary throughout our fluids books. So just as an FYI, volume will often come up looking like that. Okay, so we can plug in these values. 1,005 kilograms per cubic meter times 1 cup. Before you go look online, I will tell you that the conversion from 1 cup that you have in your kitchen to cubic meters is not there. So I looked this one up on Google. I did have to look. 1 cubic meter is 4,226.75 cups. So pretty big number, but I've set this up so that here's my density of the liquid cream. Here is the volume of the liquid cream. This is the conversion of that volume we can't, cup doesn't equal a cubic meter, so we need to convert so that we end up with cubic meters. That's right. Yeah, this would basically give us the mass, right? So cubic meters will cancel, cups will cancel, and we'll end up with the total mass here. So we end up with 200.238 kilograms or 238 grams. All right, so there's our mass. And now we need to think about what the density of our whipped cream is. So we take our mass, remember it's mass divided by volume. So we know the mass now, and we divide it by 3 cups. And again, we should probably go back, since kilograms per cups is not really a useful unit. We're going to convert our cups back to cubic meters, and we come up with 335 kilograms per cubic meter. Now, another thing that some of you may have noticed right now is all I've really done is taken a long way to taking 1,005 kilograms per cubic meter and dividing it by 3. And essentially, that's exactly what we've done. I've taken a few steps to do that so that hopefully you understand, but a shorter cut would have been to say, well, I had 1 cup and now I've taken the same mass and I put it in 3 cups. If I evenly distribute that, what is my new density? I can just take the old density and divide by 3. So fair enough. So there's our density. Now we need to calculate the specific gravity, or at least that's the first opportunity we have. So the specific gravity of the whipped cream will be equal to the density of the whipped cream divided by the density of water. So at 4 degrees Celsius, so that's 1,000. Remember, that's always 1,000 kilograms per cubic meter. And so when we work this out, we get 0.335 is our specific gravity. Pretty straightforward, right? 335 divided by 1,000. And remember, there should be no units on this, right? This should just be a ratio. So there's our answer there. And then if we want to calculate the specific the specific weight of the whipped cream, now remember our equation was the density of the whipped cream times g, our gravitational acceleration. So 335 kilograms per cubic meter times 9.81 meters per second squared will give us 3,290 newtons per cubic meter, all right? And so that is essentially the number we have. Now, real quick, if we had put water in there instead, in the water density here, right, we would end up with 9,810. So we're still, roughly a third of that, which says that it's lighter. So if we had a cubic meter of whipped cream, which might sound great to all of us, that would be about a third as heavy as a cubic meter of water. So just a little bit of a gut check there to think through some comparisons. Any questions on working those problems? Okay, great. All right, the next one's a little bit complicated. I want to go back to this surface tension example that we had in class. We did this video where you put a two-sided, really light razor blade on the water surface. It floats, and then if we push a little, we can make it fall, but surface tension is keeping it in place on the surface. And then if we put a single-edged razor blade on, it doesn't get held, right? Surface tension is not strong enough to hold it in place. So what's the deal? All right, so if we assume that the surface tension forces act at an angle relative to the water surface shown in this figure, so here's theta right here, so acting in this upward but not quite perfectly vertical direction, and the mass of the double blade razor is 0.57 times 10 to the minus 3 kilograms, and the total length of its sides is 198 millimeters, then A, determine the value of theta required to maintain equilibrium between the blade, this double-sided blade, weight, and the resultant force, surface tension force. Okay, so that's part A. Part B says the mass of the single-edged blade is 2.44 times 10 to the minus 3, so quite a bit heavier, and has a total length on its sides of 168, so also a little bit smaller in physical size. Explain why this blade sinks. Support your answers with necessary calculations. Okay, so I'm going to minimize that. We'll keep it there, and we're just going to look. Here's the blade, either of them, sitting on the surface. Obviously, we know that the double-edged one floats, the other one, the single-edged, sinks. And this is our surface tension force acting upward. And here's theta, which is an angle with respect to the water surface. Okay, so first of all right, so get your Reef app ready. And I'm going to have to pull up my, all right, I'm going to get class started here for fluid mechanics. All right, so here is our first question. And the question is, to begin this problem, we need to, A, do we need to get more information? B, do we need to create a free body diagram of the blade? C, do we need to do a dimensional analysis? Or D, do we need to create a control volume surrounding the blade? So give you guys 60 seconds to think about that. what's our best first step here? Remember that surface tension is interacting with the edge of the blade in this case, and that's why surface tension, you may recall, is force per length.
We can see the poll right now.
Yeah, I've left it up for you guys. We've got 30 seconds there. I'll take a look here. We've got somebody jumping between D and E. All right, E, not an option, but okay. I guess one of the points maybe you're making is you could be skewed now by your vote by seeing how everybody else votes. So another 9 seconds here, but we've got most people voting for B, creating a free body diagram of the blade, and as it works out, that is indeed true. So, good deal. Good job. Yeah. So, more information in the geometry of the blade wouldn't necessarily help us. We're going to assume it's something like a rectangle, but given the perimeter of it, regardless of its shape, we should be able to work with what we've got. So B is what we're going to want to do. A dimensional analysis doesn't help us too much because we could throw in some equations, but even if we just used FST, the force of the surface tension equation that we have, we still don't know exactly what that works out to try to solve the problem. All right, so let me go to the next slide because we have one more question here. And we'll get this started. Identify the major forces that influence the floating of the blade. And I think one of the problems here is, I'll just play it. I'll just let it go. But I will tell you right now, there are two correct answers here, and I don't think you can choose both of them. So hopefully we'll get both of them. Will show up in the sort of highest count here. But we have buoyancy, air resistance, surface tension, weight or gravity, mass times acceleration, and centrifugal force. So which of these matter the most? All right. Good. We've got 85 responses. We have 93 participants, so minus 3 of us. If the TAs are both on plus myself, we should have 4 more responses. Anybody's got them? All right. Okay, so C was the highest. Indeed, surface tension. This is a question about surface tension, so good. And then D will be the other one. And sure enough, that turned out to be a high one. But we're basically going to set these two equal to each other, which is key, so that we can switch out of that polling mode and go back here. Okay, so okay, give me one more second here. So essentially, we're going to deal with both surface tension and weight. I guess one of the problems, I did get this from somewhere else, one of the problems with E is that, of course, weight is mass times acceleration. It just ends up being gravity. So anyway, a little bit of a confusion on that one, but centrifugal force should obviously be like that one. Yep.
I had a question.
Yep.
So if like any object doesn't break surface tension, is it not displacing any of the liquid or any of the fluid?
It is not, because it's not completely submerged. I suppose there's an argument to make. So if you are, there's probably an argument to be made for like some amount of immersion because it's being supported by the surface tension, but you've probably deflected a little bit of those molecules right at the surface. But buoyancy wouldn't completely come into play because you haven't submerged it all the way, which is something we'll get to in a few weeks. But yeah, good question. Okay, so how do we start to handle this problem? So we know that we are at a static equilibrium, meaning that the force of the weight of the razor blade is in balance with this force of surface tension. The question is, remember, we're going back to just trying to figure out what angle here would suffice to hold the double-edged razor blade in place. So we're going to start with the sum of the forces in the z direction equals 0. We know that gravity works downward. We know that some portion of surface tension is working upward. So those two are in opposition to each other, and they should be in balance to keep the blade from sinking. So sum of the forces equals 0. Some component of surface tension is working upward minus weight working downward, which means, of course, that we can set them equal to each other. I have simplified this and not added the component, the vertical component of the surface tension weight. We'll get to our surface tension force. We'll get to that in just a moment. There is an angle term in the surface tension force equation, and it looks, for starters, I haven't put it in here yet because I want to ask you what it is. But remember, surface tension is going to be sigma. The surface tension value is in force per length. So we're going to multiply sigma by a length, in this case, the perimeter of our object, which is what was given up above. The length is 198 millimeters. And now I've left out the sine, cosine, tangent term. Which component do we need here, given the way theta is drawn? Do we need a sine theta, a cosine theta, a tangent theta to help us get the vertical component to this surface tension force? Anybody have a guess? Oh, are they coming in the chat and I'm missing them?
Fine.
What was that, Lewis?
Sine.
Sine. Yep, that is correct. Okay, so here we go. We do want the sine of theta in this case. Now, remember in your book, when we were talking about, and in the notes, we talked about a vertical column. That angle was from the vertical component of the column. So it would be opposite of what theta was, right? So in that case, we're using cosine. In this case, we're using the sine because we are looking at the component of, or the angle coming from the water up to that force, right? Okay, so now we can figure out both the surface tension force and the weight. The surface tension force we said was that from the previous slide. If I go look up the surface tension value, this is now from table B2 in your online book. And what I did is I'm just going to go ahead and grab a value at 20 degrees Celsius. That's about room temperature. And I'm writing down 7.28 times 10 to the minus 2 newtons per meter. Okay. There is another version of this that is not SI units. It's British units. If you're working in British units, that's totally fine. So in this case, 0.0728 newtons per meter is what we're going to include. So that goes there. And now we can work this out a little better. So the surface tension force is 7.28 times 10 to the minus 2 newtons per meter. We multiply by, in this case, the length that's interacting with the water is 198 millimeters as given, and then sine of theta. Remember, theta is what we're looking for. Now we need to take the step of figuring out the weight. One step further, I didn't make this conversion yet. This is in meters, newtons per meter. This is in millimeters. So let's convert our millimeters to meters. So we do that by multiplying by 1 meter over 1,000 millimeters. The millimeters will cancel, and then the meters will cancel to give us newtons. So that's a force multiplied by the sine of an angle, which of course is just a ratio. So there's no units there. All right, so when we take that a step further, we basically end up with 0.0144 sine theta. So that'll be one side of our equation. Remember the other side, going back to the equation I had on a previous slide, FST is equal to W. So now let's figure out W so that we can take this and figure out theta. So on the right-hand side is W. W is just mass times gravity, right? So we were given 0.57 times 10 to the minus 3 kilograms times 9.81 meters per second squared. And when we do that math, we should end up with, there it is, 5.59 times 10 to the minus 4 newtons, okay? So in other words, if we put these together, we said the surface tension force is equal to the weight, and that's the vertical component of the surface tension force is 0.00144 newtons times the sine of theta is equal to 5.59 times 10 to the minus 4 newtons. One thing I suppose I probably shouldn't have done, this is more or less in scientific notation, and these are not. Could have done 1.44 times 10 to the minus 3. So apologies for that. But Then if I just divide both sides by 0.00144, I end up with sine is equal to 0.3879 with a bunch more terms, right? A bunch more numbers. But if I just kind of focus on that, the theta I solve for is about 22.63 degrees. Okay, so that's essentially what you should come up with. So as long as we are somewhere in that neighborhood, we should be able to hold up the blade, all right? But part B of this question was to ask, with the single blade, now the mass is 2.44 times 10 to the minus 3. Can you find a theta that works to keep that one up? And the answer is probably, you already know from the video, is going to be no. How do we prove that? So let's go back through this process, and the only thing we'll do differently is we'll calculate a new weight, right? The new weight will be a different value plugged in here for the mass of the single-edged blade. So for the single-edged blade, let's start by calculating W. So the weight is 2.44 times 10 to the minus 3 grams times 9.81 meters per second squared. And we get 2.39 times 10 to the minus 3rd newtons. And then if we take it a step further, if we solve for theta again, that angle, remember we're still going to use the same representation for our surface tension force. And in this case, we basically keep that left-hand side. The right-hand side now becomes this. And when we divide those two, we get a ratio now of sine is equal to 1.661. Ruh-roh. Does anybody see a problem with that?
Professor, the length of different than the length in A.
Thank you. I did forget that when I was going through it. Ah, rats. I think, so thank you for that. It should have been 168. I should have plugged in. Thanks for that catch. See, if we were working on a chalkboard, I could have actually gone back and figured this out. So sorry about that. All right, good catch, Lewis. And what I think, so this number won't be the same, but you should still come out with a value of sine theta greater than 1. And the point that I wanted to make, even though this is the wrong number, is that the sine of theta can't be greater than 1 if we have an angle of theta being between 0 and 90, right? So part of the reason that this fails, or that we can't hold up the single-edged razor blade with both its smaller, in this case, it's smaller perimeter, so 168 millimeters instead of 198, which means the surface tension force will go down, and its greater mass, is because that theta value will have to be greater than 90, and that is basically undefined for this particular setup, okay? So in this case, theta being undefined sort of tells us the single-edge blade cannot be supported by surface tension, all right? Okay, I'll ask for questions on that. I realize we're at 5 o'clock, 1 minute past, and I have one more problem to go through. So if you need to duck out because you've got something you need to get to, that's fine. I will still go through this problem, this last problem that I have set up, and then post the video, and you can watch it whenever you want. If you are able to stay on, I'll go through it, and then again, we'll just have it captured in video, and I'll post a link to that video. But before I go on to that, are there any questions on this particular problem and the way it was set up? Noting, of course, that I did goof up the length. This surface tension should have been a different value over here.
Yeah, just to clarify, total length of its sides is like the perimeter of the blade?
Yeah,
Okay.
I don't know if it was also trying to count, like the double razor blade, particularly in the video, you saw there's little etchings in the middle that are kind of open. I don't know that we included that because it seems like that would be a lot more than 30 millimeters, but in any event, I just took it as the perimeter in this case.
Okay.
Quick question for the free body diagram. It looks like, from my analysis of it, wouldn't there be 2 upward forces, at least if we're looking at this image?
Yeah, that's a good question. There's not really, you're not doubling it. The representation here is perhaps a little bit obtuse, and you're getting at that, which is good. Why are there two arrows, for example, on this? And the reason is simply that truly the surface tension force is acting all around the perimeter of the object, of the double-sided razor blade in this case. And what that still comes down to is let's see if I can just draw here real quick, is, oops, sorry, go back here, is having a plate that looks something like this, having weight obviously working downward, right? And then all of that surface tension that is working around the edge of the blade is really, FST, and then maybe to be more careful about this, we should say times the sine of theta. And by the way, I'm writing with my mouse, which is incredibly dangerous. So the fact that has come out that clear, I'm pretty proud of. But in any event, all the arrows around the edge are still summing up to a single force acting in the vertical direction. Does that make sense?
Yeah.
Got it. Great. Okay. Good. All right. Any other questions on this one? Okay. I'll go on to the next one then. And I think, if I recall, I haven't done this in a while, I think I have to go and get rid of my doodle. Well, this is weird. If I can get my cursor back, where do we go? This is strange. Oh, there it is. Okay. So if I recall, I need to erase or, clear. There we go. All right. Now we go to the next one. Otherwise, it would hang out there. Okay, the last question that I have queued up here is a problem on shear stress. And this is more complicated than the ones that we've talked about in class, which is why, and more complicated than one you've had in homework, which is why I wanted to go through it. So a Newtonian fluid, and by the way, we didn't talk much about Newtonian and non-Newtonian fluids. Newtonian fluids are ones that will deform more when we provide more shear stress at the surface. So, for example, honey is not a bad one. Water, oil. When we get to things like peanut butter, you now have a certain shear stress you have to overcome before something moves, for example. So, there might be some other ones we could think of, but in any event, sometimes we qualify this as saying a Newtonian fluid, meaning that it should move as soon as we apply some stress. So a Newtonian fluid having a specific gravity of 0.92, so we don't know what the fluid is, and a kinematic viscosity of 4 times 10 to the minus 4 meters squared per second, flows past a fixed surface. Due to the no-slip condition, the velocity at the fixed surface is 0, so that means down here at the bottom, velocity is 0, and then the velocity profile near the surface is as shown. So it looks curved, and essentially it is described by this equation. So little u, the velocity at any location as a function of y and total depth delta, and the velocity big U at the very top of this is given by this expression. Okay, so little u divided by big U, the velocity at the top, is equal to 3/2 y over delta. So y is whatever height we are for a u that we want, minus 1/2 y over delta. So whatever height we are divided by the total height of the fluid here, delta. And then that is raised to the third power. Okay, so determine the magnitude and direction of shear stress developed on the plate. Okay, so I gave you a couple of representations of our shear stress. And I want to go back to one that we talked a little bit about, but I think we're going to get more familiar with here. So I've just shrunk the font size on our problem statement, so that's now at the top and a little bit out of our way. We still have it to refer to if we need to. We have the diagram on the lower right to refer to. And then, more importantly, we now have this relationship, which is something I gave you in class that we didn't talk too much about. So the shear stress, tau, on the left-hand side, will be in dimensions of force per area, all right? So we could work this out in either SI or British units. we're given meters squared per second for our kinematic viscosity. I told you we wouldn't work too much in kinematic viscosity. I've broken that rule a little bit here, but in part, I'll show you why it's kind of helpful in this particular instance. So tau is equal to our dynamic viscosity, mu, times du dy. So the velocity, the derivative of the velocity or the slope of the velocity profile right at u equals 0, okay? So what we're going to do, as you can imagine, is take the derivative of this equation with respect to y and plug it into this parenthesis, and then we're going to figure out how to deal with mu as well. So the first thing we're going to do is re-represent that equation for the velocity profile in just terms of u, okay? So little u, because that's what we need to take the derivative of. Big U is actually a fixed value. We don't know what it is, but it's some value at the very top of this profile, right? So all I do is, well, shoot, did I do that? I did that wrong. I didn't distribute that all the way through. My apologies. I just typed it on the right-hand side. So there should be another U in front of this side as well, or a parenthesis here over this entire thing, right? I meant to multiply both sides by big U, and I goofed that up, so sorry about that. All right. The next step then would be to take the derivative of this with respect to y. And when we do that, now I've got U on the outside, so I missed the parenthesis up here, but I put it in down here. So du dy is equal to big U, and then the first term has a 3y in it, right? So we're going to get 3 over 2 delta minus, and then we had a y cubed in the second term. So now we're going to have basically this 1/3 comes through, but when we work through with this 1/2, or three times, sorry, we're going to end up with the 1/2 y over delta. Delta remains cubed. All we've done is distribute this. We had a y cubed over a delta cubed. So delta cubed stays in the denominator. We end up with 3/2 y squared over 2 or over delta cubed. And remember that we want this at the surface. We're asked at the surface. So y equals 0. So now we can plug in y equals 0 here to simplify this. So at y equals 0, du dy is equal to u times 3 over 2 delta. All right, we can simplify that to 3 capital U over 2 delta. So now we're in terms of big U and delta, wherever we are throughout this, but really it's about this particular slope right at y equals 0. If we were at y equals 1 millimeter, we would have a different slope, right? We should come up with a whole different value. But in any event, we're asked to express our answers in terms of u and delta. So we're partway there. This term, when we plug it in here, is going to be in terms of u and delta, but we still have this pesky mu. So what do we do with that? Well, the hint that we need to do something with that, this mu, is that we were given a kinematic viscosity and a specific gravity, okay? So one solution you might say is, well, Dr. Gusev, why don't we just look up a mu, right, of a dynamic viscosity? Well, the problem is we don't know what fluid this is. All we know is that it's a Newtonian fluid. We weren't told whether it was a type of oil, water, honey, whatever, okay? So we do need to deal with some relationship between the kinematic viscosity that was given and the dynamic viscosity. So we do that by basically recalling that mu, our dynamic viscosity, is divided by density is equal to our kinematic viscosity. Or if we multiply through by our density, we end up with mu is equal to nu, our kinematic viscosity, times the density. So we can now rewrite this and plug this equation in. We get, and what we had on the previous slide for du dy, we end up with tau is equal to nu rho 3 capital U divided by 2 delta. And now we can plug in numbers for both nu and rho, all right? So we don't have a density, but we do have the specific gravity. So the density of our fluid, we said, is just 0.92 times the density of gravity, or pardon me, the density of water at 4 degrees C, which is 1,000 kilograms per cubic meter. So if we take that a step further, this would just come out to be 920 kilograms per cubic meter, right? So that's that multiplication there. And then we were given that the kinematic viscosity is 4 times 10 to the minus 4 meters squared per second. So when we plug all of this in now, we get 4 times 10 to the minus 4 meters squared per second. So there's our new. Our density is 920 kilograms per cubic meter. And we still have our 3 halves. I've separated it from the U over delta. And the only reason I did that is that I can multiply all of these things in the numerator together and all of these things in the denominator to basically end up with some number in front of U over delta, right? And when I do that, it turns out that you end up with 0.552 U over delta. And there are 2 ways of figuring out what these units should be on the right-hand side. You should be able to combine all of these on the right-hand side, all of these units, to almost figure it out. And the reason I say it's almost is don't forget that U, capital U here, will be in meters per second, probably. That's what we would expect working in SI. And that delta here will be some height in meters, right? And so you just need to include that, but you should come out with newtons per meter squared. And so the only other point I make is that would be the expected tau unit equivalency when you're working through a shear stress problem like this, because it should be force per area. All right. That concludes what I had for recitation today. I apologize for taking an extra 15